Welcome to the MRI section of the course. We're going to switch gears here a little today. But before I get started, are there any questions about course logistics or anything? Okay, so we'll have two MRI lectures this week, and then next week our project presentations. We'll be sending out more info about those, but the basic idea is half of the groups will present live, the other half will present to submit videos just because of the size of the class. And for those of you presenting live, and we'll post information about this, but you will be still presenting over Zoom. So that way we can just, instead of having to, do all the computer switching to the screen, my computer will be hooked up to the display, and then people will just change sharing screens. And so that's one of the things that came out of the pandemic is like, we know we can use Zoom for things like that. Okay. Or in the past, we would spend like 1 or 2 minutes switching computers or things like that. All right. So if anyone has questions about the projects or anything, just feel free to ask either me or the TA team. All right. So today, so let's get started. So today we're going to cover at least, maybe 3, 4 to 5 of these topics. We're going to give you an overview of what our MRI system looks like, and then hopefully get into spin and magnetization, precession, and a little bit of RF excitations. We'll see if we make it to the transverse and longitudinal components. These are the sections in the textbook that you can read along with if you need more background. So first off, this is what an MRI system looks like. And this is not the only design for an MRI system, but it is the most common design, which is it's basically a long tube that the patient lies on the patient table and then goes into the MRI system. There are 3 coils that you have to know about in an MRI system. The first one is the magnet, okay? You're going to have this huge magnet, and we'll talk about how big that magnet is. That creates a very strong magnetic field. There's going to be what's called the radio frequency coil, which sends energy into the sample or the body, and then also receives the signals back. And then there is going to be these gradient coils, which allow us to do the imaging, which is essentially going to allow us to sort of implement a Fourier transform actually in the subject itself, okay? So this is the magnet coil. And so it's basically every coil, every wire is made up of superconducting material. And so the most traditional design for magnets now is you have a lot of windings, typically a solenoidal winding of this superconducting wire. And so that's the wire is shown here. These are what's called the main windings. And all this, I guess, is it the blue stuff? Or anyways, there's the magenta stuff, I guess, is the helium in this case, okay? So essentially, to be superconducting, it has to be cooled down to really, really low temperatures. And so we need helium, okay? And that's what keeps it. Liquid helium is what keeps it at a very low temperature. And so the idea is with these magnets is when they're installed, they come in, you hook them up to the wall, you charge them up, okay? And then once you're done charging it up, you can unplug it. And if it's superconducting, then the current just keeps going, okay? So that's the basic idea. So for the remainder, for the MRI section, you will have to get familiar a little bit with units, okay? So the 2 main units we'll use are Tesla and Gauss, okay? And Tesla is named after Nikolai Tesla, not the car. So he was a very famous inventor in the early 1900s. And Gauss, as you know, is named after Carl Friedrich Gauss, the famous mathematician. And so just to get a sense of what these units are, the Earth's field here in San Diego is about half a Gauss. Okay, so if you need a sort of a reference of how strong a field is, you just remember that the Earth's field is half a Gauss. Okay, or it's about 50 microteslas. Okay, and so that sort of gives you a sense of how strong these fields are. Okay, so typically for the main magnet, we use Tesla to say how strong the field is. So 3 Tesla is currently now sort of for standard clinical imaging. If you're at a sort of a premier site like UCSD, most of our scanners here are 3 Tesla scanners. We do have some lower field scanners. So if you go to the hospital, then you'll most likely get scanned on a 3T scanner. Okay. And this is also what we have here for research, typically is 3T scanners. But as you can see, there are stronger scanners. So there's now about 100 of these 7 Tesla scanners across the world. There's one of these in Chicago. There's a 10.5 Tesla in Minnesota, and there's 11.7T at NIH, and one also in France. Okay. And so one of the things we're going to talk about is why do people keep building these bigger and bigger scanners, right? This is just showing you the distribution of scanners from 2001 to 2015 to 2019, and this was about 5 years ago, so there are about 100 of these systems. There's probably more now, but I'm not sure how many more there are now. But as you can see, 3T scanners are by far the most prevalent scanner currently. So this is a picture of the 11.7 Tesla scanner, and you can sort of see it's a beast, right? These are people standing next to it. Okay. So in fact, they basically had to build the floor here so that people don't have to climb a ladder into it. Okay. And then this was just actually published literally last week. Okay. These are the first human images off that scanner. They've been working on this scanner for I don't know how many years, maybe 20 years or something. So it's a tremendous undertaking to build this scanner. And so the idea is if you zoom in on this, let's see if we can zoom in on this. So these are some images at 3 Tesla, 7 Tesla, 11.7 Tesla. And you can sort of see here the level of detail just increases as you go to higher field strength. Okay. And so that's sort of the push is that what we'll find is the more you increase that field, the more signal you get. And so that the hope is that will allow you to get more information. So for example, here, does anyone know what this area of the brain is called? Yeah, cerebellum, right? So this is the area that if you didn't have this, you wouldn't be able to walk or do anything, essentially. It's a really important area. And so it's got all these amazing little folds in it that you can see very nicely in this image here. Okay. Um, So yeah, and so because this is the first of its kind to really be used on humans, they had to do a lot of testing on it. So they said physiological, vestibular, and cognitive measurements were implemented in the protocol to verify the innocuousness of the large magnetic field on humans. Across all tests carried out in this protocol, the statistical analysis revealed no significant difference related to field exposure. So that means that no one died and everyone seemed normal after being in the magnet. So that's good. Okay. Now, there is one thing that if you are close to one of these magnets, that is that if you ever go near not so much a 3 Tesla, but anywhere like 4 Tesla, 7 Tesla, 11.7 Tesla, if you shake your head, especially near the opening of the magnet, you can get very nauseous or dizzy or even see flashes of light. And so what happens, so going back to freshman physics, like if you're in a magnetic field and you move in a magnetic field, what's created? Yeah, electric fields, right? Maxwell's equations, right? E is proportional to BDT. So basically, if you do that, you're actually creating currents in your head, which messes with your brain. So that's one of the. So when you go into one of these magnets, you have to move sort of slowly. Otherwise, bad things could happen. Okay. This is one of a cutaway of the magnet, that big magnet, and the stored energy. We'll just look at one thing is here is that um, it's got 338 megajoules of energy in it, okay? Which seems like a big number, but it's equal to about maybe 3 gallons of gasoline, okay? Or, how many, you know, a lot of kilograms of TNT, or you could drive a Tesla for about 338 miles on that much energy. Okay. So it's not out of the realm of reasoning, but if you're to release that energy very quickly, it would just blow things up, right? I mean, so if you use it over time, then it's sort of comparable to, you could drive around for a few hours on that much energy. The other thing is these are some different magnets from this paper, and what you'll notice are the weights. So this one weighs 110 tons, 132 tons, 60 tons, and so these are really, really huge things. Okay, so part of when they build these magnets, the main thing they have to worry about, or whenever we're installing a new magnet, we have to make sure the floor can support it. Okay, so it doesn't collapse the floor. So these are some pictures of the magnet at our facility. So what you see here is this is a magnet that's being decommissioned. And this gas is basically, we're trying to bring this down to field. Okay, so we're going from 3 Tesla and ramping it down to 0 Tesla, or turning off the field so we can move it. And so what you're seeing here is they're blowing off the helium. Okay, and so that's the helium coming out. And then a crane is used to lift the new magnet into place. And then it comes partially filled with helium. And so we have to add some more helium to it. And then they ramp up the magnet and bring it up to field. This is sort of what it looks like when it's done. It looks like it's just a really nice sort of design. And underneath here, if we take away this part, it's all this electronics. Okay. So in the old days, they used to put all this electronics in another room, but most modern magnets will have the magnet and most of the electronics are right here, and there's some other electronics in another room, right? So that's sort of the general layout. So one of the most important things that you can learn from this course is magnets are dangerous, okay? So if you learn nothing else, you need to learn that, first of all, a common question is, how do I know if the magnetic field is on or off? Because it doesn't make a sound, right? Magnetic fields don't announce themselves and say, I'm on, right? So you should always assume that the magnetic field is on, all right? And if you forget that, things like this can happen, okay? So these are some examples of people bringing things into the magnet room, and the object will be very quickly pulled into the magnet, all right? These are incredibly strong magnets. They're so strong that if I gave you, say, a wrench, does everyone know what a wrench is? Okay, it's like a metal tool. Okay, so if I gave you a metal tool and you walk towards the magnet, it would be ripped out of your hands before you knew it. Okay, um, and and mostly the time that people are killed, unfortunately, is when people forget. So this was from 2021. About once a year, I think every year, about 1 or 2 people die because someone forgets. And so if you carry an oxygen bottle in, which is very common in hospitals, and you bring it into the magnet room and it gets sucked into the magnet and someone's lying in the magnet, that person will basically be killed. Okay. So if you are getting an MRI scanner or MRI scan done on you, let's say you're in a hospital, I would strongly recommend, this is what I do. They will give you, you can have the option of having a mirror to see what's going on. Now they're trying to get you to, now they're trying to say, well, that you can have a mirror looking backwards so you can sort of see nice surroundings and stuff. But if you have the option, I would still strongly recommend, having a mirror so you can see what's going on. And if you sort of notice something that you don't feel comfortable with, just say something, right? Because that is your life. So I think if you remember nothing else from this course, just remember the magnet's always on. Now, when you go into magnet room, it will make a sound going like that. That's just the helium pump sort of trying to capture the helium and put it back in. But we can turn that off, right? So even if you don't hear that sound, the magnet is still on. Okay, so just remember that. This is a great video to watch. I'm not going to take the time to show it here, but here's the YouTube link. It's a fun video to watch, so I definitely recommend watching this video. Okay, so we're going to do a little thought experiment here. So we're going to pretend you took this course, but you ignored everything I just said. Okay, and you walked into the magnet room and you are carrying this big piece of metal. Okay. So we said that this metal would be ripped out of your hands and sucked into the magnet, right? So the question is, let's say it's ripped out your hands at point A. Okay. Where does that, what happens next in time? How far is this magnet going to go through? Is it, any thoughts on this? Is it going to go to point B, point C, point D, or point E? What do people think? Yeah, go ahead.
Probably point B.
Okay, so vote for point B. It's going to just go to the edge of the magnet. Okay. Why will it stop there?
I think it would stop when it touches the magnet.
Okay, well, let's say there's a hole in the magnet, right? There's a bore of the magnet. So there's nothing stopping it from going through the hole, right? Because that's where the patient goes through. Okay, so right, there's a hole. I should draw that. There's a hole here in the magnet. Okay. Okay, so does that change your answer?
Yeah.
Okay, okay. So yes. Do you want to revise your answer and then I'll get to you?
Sure. Then it just accelerates and goes through, I guess.
Okay, so where will it end up? Far out here.
Yeah.
Okay, go ahead.
I was gonna say C, because
Okay,
probably where the center of the magnetic field is.
right.
My assumption is once it hits the center, it might hit equilibrium
Okay,
somewhere around there.
good. And then the center of the magnet, just so we start introducing terminology, is what's called the isocenter. That is, there's a center of the magnet. Okay. Any other thoughts on where this will go ahead? Over there.
I think it's going to E and pulse back.
Okay, you could think it's going to go E and then come back. Why do you say that?
Because after you go through this tube, the magnetic force will start to pull it back,
Okay.
just like as pointing.
Okay. Okay. Good. Was there someone here? Yeah.
So that I think you'll kind of go A to E to B to B to so on.
Okay. So it's going to sort of go oscillate, right? Okay. Yeah. So something went in the back? Just what he said. Okay. Yeah. So the later answers are basically correct, right? Because you think of it, there's some potential energy here, right? And the other point of equal potential energy is E, right? So if there's nothing, if it goes on a straight line, it will fly right through the magnet. And then guess what? It's coming right back at you. Okay. And if you're lucky, it'll go off at an angle, right? If you're not quite in the center, it'll be pulled off and it'll hit the magnet and maybe hit the sides and it'll rattle around and may not come back and hit you directly. But if you're really unlucky, it will actually, before you know it, your hand will be gone. Okay. Because it will have come back and hit you. Okay. And I know of people where they've had injuries, but luckily they've not lost anything. They got lucky because they weren't perfectly right in the center. But if you're perfectly right in the center, that's what could happen. Okay. So I hope I've scared enough of you, all of you, to respect the magnets. Now, that said, if you're careful, and I mean, I've been working with magnets for over 20 years, as long as you're careful, you can work with a magnet. Okay. But if you forget, then it is very dangerous. All right. Okay. Any other questions? Okay, so the other thing we need to talk about with magnets is we've talked about the main coil, which creates a magnetic field. But especially, if you want to put a magnet in a room, then you don't want these fields to go too far. Okay, because then people say we put a magnet here and someone's walking through the hallway. Once again, they're walking through a magnetic field, right? And so as they're walking through the magnetic field, they're causing electric currents in their body. Okay. So, and especially people with pacemakers, for example, especially in older design pacemakers, that could or any medical device which you're causing interference in could be a problem. So there are very strong, there's two things that we do one is we have a counterwound cable. So if these cables were going wound this way, these cables will be wound the other way. So they basically cancel out the magnetic field, do their best to try to cancel out what's called the stray magnetic field, right? And so for every magnet you get, you sort of have these plots of magnetic field lines. And what we're typically looking at is where's the 5 Gauss line. Okay, how far does that stray out? So remember, 5 Gauss, Earth's field is half a Gauss. So we're typically looking for where is the magnetic field 10 times stronger than the Earth's magnetic field. Okay. So we want to fairly quickly go from 30,000 Gauss, in this case, down to 5 Gauss very quickly. Okay. And this is what's called the fringe field. Okay. And so you can sort of see this magnetic field is changing very quickly. So that's why if you walk through this field, and this is a very strong field, the forces here are very, very strong because whenever you have a changing magnetic field, that creates forces. Okay. And that's why, for example, if you were holding a wrench, you could be here and think everything is fine, right? There's really very little force here because the fields are changing relatively slowly and they're relatively weak. But once you cross, there's like a danger zone. Like once you cross, like you take one extra step and all of a sudden you're in the danger zone because the fields are changing so quickly that that's where it gets ripped out of your hands. So basically, for example, as a sort of a real life experiment, this is maybe, yeah, 3 years ago, we were installing a new magnet, and when we did all the simulations, we realized that the magnetic field would protrude out into this public walkway. And even though we had a big piece of metal back here, iron, to sort of reduce the field, it was still going to protrude out based on our modeling. So in this case, this is what the field, the 5 Gauss line would just extend a little bit into like even less than a foot into the public walkway. But because of the regulations, we still had to make sure that that 5 Gauss line didn't go into the walkway. Okay. So in this case, the solution was pretty easy. We could just move the magnet field a little bit this way, away from the wall, such that the 5 Gauss line stayed within, wasn't in the walkway. So that's one of the design things that we had to do. Okay. Now, there are other designs. So we've talked about sort of this classic design where you're going through a tube, but there are designs here where, for example, like a pancake design where you have magnets on top and below, and so there's an open space here. And then you also have this where there's 2 sort of donuts here, and the magnetic field is going this way. Okay. So these are sort of what are called like open MRI designs where they're very useful. For example, you can imagine if you just had to have your hand scanned or your leg scanned and you're claustrophobic, that this would be a much sort of more friendly environment. This has the advantage that if you wanted to like look at someone's back, so experiments where you're looking at back pain and stuff, you can have them stand up or do flexion and things like that. All right. They tend to be lower field because it's just harder to get strong fields. The other application of these types of magnets is if you wanted to do MRI in the operating room. Okay, so then you have more access. Yes, question. You mean for the RF? Yeah, that's a good question. I mean, you can always sort of have sort of RF coils, but that's a good question. I don't really actually know what the body coil configuration is for these magnets. Yeah. Yeah. Typically these wouldn't be used for brains. They're typically used for like extremities or looking at the spine or something like that. So if you really wanted to have a brain exam done, you would probably just go to a regular magnet. Or I can show you, there'll be some other examples we can show you. But that's actually like even though you're thinking about your CT projects now, thinking about the MRI projects, looking at open MRI designs certainly would be something that we're not going to cover too much in this class. So that's certainly an interesting area to look into. The other thing that every once in a while we have to worry about is these helium shortages. So there's not much naturally occurring helium, and so a lot of the helium comes from nuclear facilities, where helium is being produced due to reactions, and every once in a while, and a lot of this depends on government policies and whether those policies, what they say, but there is sort of this concern that there may not be enough helium to continue building MRIs the way we've been building them. Okay. So that's led to, for example, a classic magnetic technology would require 1,500 liters of liquid helium. And not only is it expensive, but it's becoming more scarce, right? I forget when it was, but maybe like 5 years ago, it was so scarce that you couldn't even go buy helium balloons at the party store, right? There was like a ban on helium balloons, right? So manufacturers have been doing a lot of work to create sort of designs that use much less helium. So this only used like 7 liters of helium. This one only uses 0.7 liters of helium. Okay. And that's because they've learned ways of essentially other refrigeration technologies of getting the heat out. Okay. And so as these technologies develop, then hopefully there'll be less need for helium. The other thing that you'll notice is the manufacturers are starting to look at different sizes. So for example, because of certainly in certain parts of the world where people tend to be bigger, then it's advantageous to have a much bigger bore. Like typically a bore might be 60 centimeters. This is like an 80 centimeter bore. Okay, so much larger bore. Or for other applications where, for example, you want to scan babies, you don't need a big magnet, and so you might design something with a smaller bore. And you make it smaller so everything is easier to do, and it can be easier to cite, and it's less expensive as well. Okay. And then there are developments, for example, in sort of better magnetic wires. So, going to these new chemical high temperature superconductors is also going from a magnet this size, you can go to a magnet this size because the current carrying capacity of these new materials is higher, and so you can sort of run more current through the wire. Okay. And so you can sort of see here that the weight goes from here down to a much more manageable weight. So those are some of the things that people are working on. And then the other direction is, especially with development of AI, and we'll get to this later in the course, that we can use AI to make images even if the underlying data is not as good. Okay. And so this is a magnet that's actually developed by a company called Hyperfine. And this is only at 64 millitesla. So it's a very low field. And this magnet is something that you literally can, it's on wheels and you could roll it around, plug it into the wall. We could bring one in here and we just start scanning people. In fact, this is me being scanned on the floor of a conference, and they were just letting people put their heads in and get scanned. Okay. And so as I'm being scanned, they have an iPad hooked up to it and communicating with the magnet, and the images are coming in, and these are images of my head, and they actually look pretty good. I mean, in terms of image quality, I mean, they're not as great as you could get with uh, a clinical magnet, but they're certainly um, if I had like a concussion or I had some fluid in my brain, they would certainly be good enough to detect something like that. And so one of the questions is, is there a place for these in the healthcare system? Like, do you always need the best magnet possible? So if you're at an academic center like UCSD, we always want the best, right? Our radiologists will always want the best equipment so they can make the diagnosis of even the most rare case. And so that's great. But if you're in a country that may not have much infrastructure, um, then there might be an advantage to having these sort of good enough magnets spread out across the community. So for example, I believe the Gates Foundation has bought 20 of these, and they're doing a pilot study in Africa right now and sort of seeing the application of these low field magnets. And so this is also, if you're thinking about projects, this is also sort of a really interesting emerging area to get into. Okay. Like what are the trade-offs they make for, doing these really ultra low field magnets? Okay, so that's sort of an overview, and we've talked about the main field here, which is creating the magnetic field. Now we're going to transition to RF, which is basically short for radio frequency. Right. So typically there is what's called a body coil. And its job, so we talked about this magnetic field, which we will refer to as the B0 field. So in this class, anytime you see B0, that's the main field. And then the B1 field is the RF field. Right? And also, just so you know, I will post a copy of the marked notes to Canvas later. So all these annotations you can look at as well. I mean, feel free to make your own, but just in case, they will also be here. And also, the other thing I want to point out is a lot of these slides use things from this awesome website called MRIQuestions.com. It's run by a retired radiologist. It's it's a great site. So if you're doing projects or you're confused, obviously you can ask ChatGPT as well. But MRI Questions is just a really good website as well. Okay, which probably ChatGPT probably grabs stuff from MRIQuestions.com. But just so you know that this is a really good source of material. And so we'll talk a little bit about what the job of this field is to do, and how it works. But the main thing to realize is RF comes in both the transmit and receive. Okay, so the RF is going to both put energy in and it's going to listen for the energy out. Okay, so that's sort of how we talk to the sample. All right. And this is what a coil looks like. This is what's called a bird cage design, and it's typically a bunch of copper strips with some electronics. Now, there's always going to be typically in most clone scanners, there's going to be a main coil here. Okay. And for many years, really, this was sort of the primary one. There might be one for the body, or you could design, there might be another one, that you could do for the head. You could design a smaller coil that would both transmit and receive. Okay. But over the last 20 years, there's been a huge revolution in having lots and lots of little receiver coils. Okay, so these coils here are receive-only coils. They don't transmit. All they do is receive. Okay, and we'll get into why that's really important as we get into the class. But just so you know that, and these coils look like this. And so the nice thing is now you can start thinking of locally receiving. And as you get closer to the body, then your sensitivity to the signal also increases. These are just some examples. So you can these are like homemade examples. They're not clinical examples, but you can sort of see they're all fairly simple. It's just a bunch of copper and some sort of typically capacitors and resistors, and you're just trying to sort of tune it up to receive the energy. This is an example of an array coil. So here, there's lots of little receiver coils in this that are covering the entire body. Okay. And this is an example of how things go from academia to industry. So this is the prototype version of a coil, and you can sort of see each of these is just a copper loop, and it's connected to a cable, and each of these is a receive-only coil. Okay. And then after they showed that this worked pretty well, then they worked with Siemens, and this is now sort of the commercial version of that coil. Okay. Obviously a lot more ergonomic. Okay. But every coil starts off like this. Okay, typically. Okay, so that's the RF coils. We'll get back to that. Now, the next coil we want to talk about is the gradient coils. All right. And so for the most standard magnets, there's going to be three sets of these. There's going to be an X gradient, a Y gradient, and a Z gradient. All right, and their job is to create a gradient in either the X direction, the Y direction, or the Z direction. We'll talk about why we need to do that later, but for now, I'm just giving an overview of what the coils are there. This, I believe, is from the Siemens factory floor, an example of sort of the intricate coil designs that they use to introduce these gradients in the field. And then just to define mathematically what these are is the gradient is always going to be with respect to the Z direction. Okay. So, and so let's actually start defining some coordinate systems here. So for classic design, the direction of the B naught field, we're going to call that the Z axis. Okay. So that's just by convention. Okay. And then transverse to that axis are then the XY dimensions. Okay. Whoops. Cancel that. And then so we're going to have a main field B0. And then you can imagine you can add on, there might be some variation of that varying in the X direction, the Y direction, and the Z direction. Okay. So these are like dBdz, dBz, delta BZ over delta X, delta BZ over delta Y, and delta BZ over delta Z. Okay. So for each of these, let's look at, for example, the gradient in the Z direction. So if the Z direction is going this way, and I have a positive gradient, that just means my Z component of my field is increasing with the Z direction. Right. If I have a Y gradient, and the Y direction is this way, that means as I go along this way in the Y direction, the Z component of the field is increasing. Okay, so that's all we're talking about. And so we'll find out as we go through these lectures that being able to do this is the key behind how we can make an MRI image. So the simplest way you can create a gradient, for example, is you could have a coil with current going this way, and another coil with current going this way. So this was going to create a magnetic field going this way, and this would create a magnetic field going this way. And by superposing the fields, the field here is going to be zero. It's going to get more positive this way and more negative this way. So that's a Z gradient. Okay. So notice we can have, because it's a Z gradient, you have both positive and negative with respect to the isocenter. So once again, here is what we call the isocenter. Okay, so by definition, that's the center of the magnet. It's also where those added gradient fields are equal to zero. So the isocenter never has any added fields to it ideally, right? But much more for the XY gradients, there's something called Golay coils. This is the simplest implementation of those, but in practice, there's really these very intricate designs that are essentially computer designed. Basically, an algorithm figures out what sort of coil layout will give you the right gradient, right? Okay, so, and then these gradients are driven by gradient amplifiers, okay? And these are like these are like beasts. I mean, these are typically, there's a whole cabinet typically, or at least half a cabinet of an MRI system devoted to these. And so let's look at some typical values. So a typical gradient would be 5 Gauss per centimeter, okay? Or 50 millitesla per meter. This means that if I go 1 millimeter, the field changes by half a Gauss. Okay, so the Earth's magnetic field about. So it's really not that much of a change, but it's enough that we can make images with. The slew rate refers to how quickly we're changing that field. So rise time might be this slew rate, which means that we go from 0 to 5 Gauss centimeter in 250 microseconds. So we can do that pretty quickly. And that's really important because, as we'll find out, time is of the essence in MRI because the signal starts decaying, we'll see. And so we got to go through and get that signal very quickly. So to go that quickly, starting in really in the 90s was really the biggest sort of push where people started being able to do this really fast, was they really need to create these very strong amplifiers. So a typical amplifier would be like a 1 megawatt amplifier. Just a lot of power. So like typically these will have, maybe like 1,000 amps, 200 volt, or basically high voltage, high amperage. And just so you, as a point of reference, this is a pretty old fact, but if you wanted to power like a rock concert, I think this was the Metallica World Tour. It was 367 megawatts. So one of these would be sufficient to power a rock concert. Okay. So it's a lot of power. So that's the other, if you are working around an MRI system, that is a very high power thing. Definitely don't want to touch it. It's got a lot of power in it. Okay, so let's sort of sum up what we've talked about. So and then what we're gonna do in the remaining lectures over the course of the next 5 or 6 weeks is we're gonna sort of talk about what each part does. But we have a magnet, okay? We're going to have something that controls the radio frequency field, okay? And so that's going to put energy in and also receive data out. And so that's going to get digitized, and we're going to make images, and we'll store those images. And the other thing we have is what's called the pulse program measurement system. And what this does is it controls both the RF and the gradients. Okay, so basically I'll have some RF waveform, I might have some gradient waveform over time. And this is what most of the research in MRI done in academia is on. I mean, there is stuff done on the hardware, but by far most of the research is done by just controlling the software. Okay. And because we have exquisite control, and that's done with this gradient pulse sequence program. And so by doing that, it means that with MRI, by just changing that program, you can acquire lots of different types of images. So for example, these are anatomical images. These are images of sort of iron in the brain. This is an image of the vasculature. This is an image of the white matter tracts, the wiring of your brain. And these are some images that are used to create measures of oxygenation fluctuations in your brain. So we'll touch upon most of these as we go through the course. And the idea is each of these is using the same system, but we're just changing how we apply the RF and the gradients. All right. So hopefully you'll have some idea of how that works by the time you're done with this portion of the course. And one thing that's being done is that now a lot of this with improvements in electronics, this is a group that was just showing that they could put all that stuff into like just a fairly simple board and hooked up to a PC. And so especially for these ultra low field things where you want things to be ultra portable, being able to have everything in a small footprint becomes very important. Okay. There is a push in healthcare there's sort of two pushes, right? In research, you're always going for stronger and faster and better. But in terms of clinical care, like you're looking at what benefits most of the population at the best cost. And so then there's a push to what's called point of care, POC. Like if you can put these in, your Walgreens or your CVS, just the same way you can get your vaccine right now at pavilions or wherever, then you can actually start affecting more people as opposed to having people have to come to UCSD or go to a specialized facility. So that there is a trade-off. And so it makes medical imaging a really interesting area because you can sort of decide what area, what part of that spectrum you're most interested in working on. Okay, so now we're going to start slowly diving into some of the more details of what's going on. So we're going to break, there's four main topics you sort of have to get familiar with that an MRI system does. Okay. The first is called polarization. Okay. Am I recording this or did I forget? Okay, it's probably too late now. Yeah, I think I am. Oh, wait, let's see the chat. It's recording. Good, thanks. The first step is polarization. So that's the first thing we're going to try to understand. And that's the job of the main magnet, is to create what's called polarization. The second step is excitation. And that's the job of the RF coil on the transmit side. The third step is encoding. This is what does the Fourier transform, and that's what's done with the gradient coils. And the fourth step is integration and receiving, and that's done with the RF coil on the receive side. All right, so those are the four main things. And if you understand those four things, you'll have a pretty good sense of how MRI works. Okay. But you can sort of see, as compared to CT, where there's sort of like just one thing you need to know, which is basically, the projection slice theorem. MRI, we have to sort of build it up until you understand these parts. Okay, so the first thing we're going to do is we're going to just review or just introduce the idea that the whole basis of MRI comes from the fact that elementary particles have something called spin. Okay, and that's this whole topic of quantum mechanics. So we're not going to be able to go into that. We're just going to assume that there is spin and that this is related to the intrinsic angular momentum of elementary particles. Right. And the way you can think about it is that if you have it, and this is what we're going to call an analogy. It's certainly not what's, we can't really talk about what elementary particles are or aren't. But a very simple analogy might be to think of if you had a charged sphere, right? Like you could create a ball and put a bunch of charges on that. And if you spun that sphere around its own axis, then you have charges moving around, right? And so that's essentially a current, right? And so we know from basic E&M that that would then create a magnetic field, okay? So what that means, if you have a charged particle with some angular momentum, there's also going to be a magnetic moment associated with that, okay? And those two things become very important, that the particles, the protons, have both magnetic moment and angular momentum. And those two things, and I realize now I forgot to bring the prop I wanted to bring, so I'll have to bring it next time. Does anyone have a bicycle wheel? No? Okay. All right. Yeah, sorry. I usually remember to bring that. I forgot to bring it this time. Okay. So, and the key is that the mu is the magnetic moment. and the S is the angular momentum. Okay, and those are two related by this ratio we call gamma, which is a gyromagnetic ratio. So these are some nuclear spin rules, and for this course, we'll be focusing almost exclusively on the hydrogen proton. Although certainly for projects, if you want to delve into some of these other sort of things that have MRI properties, you're welcome to do that. But most clinical imaging by far is based on proton imaging, okay? Because there's so much water in your body, there's just lots of signal, all right? And this has spin 1/2. And so let's look at a classical magnetic moment. So let's say you had just a loop with a current going through it. Then if I had something with the cross-sectional area of A, and it had a direction vector n hat and a current I, then the magnetic moment mu hat would point in the same direction, would point in that direction. Okay. So the first thing we want to review is, or have a sense of is, if I put this coil in a B field, okay, it's going to have a preferred state. And you can think of it different ways, but the bottom line is it will have its lowest energy state when its magnetic moment is aligned with the main field. And it will have its lowest and maximum energy state when it's anti-aligned. Okay. So it's going to have a preferred state. Okay. And everyone has experienced this. I assume everyone knows what a compass is, right? And so every time you use a compass needle, essentially this is what's happening, right? The compass has a magnetic moment, needle is a magnetic moment, and its lowest energy state is when it's aligned with the main field. If you could turn the compass needle so it's anti-aligned, right, it would just go back to its lowest energy state, right? So it has a preferred state. So same thing when you put a human body into a magnet, the protons will now have a preferred orientation. And we're going to, the probability of you finding something in a state is going to be defined by what's called the Boltzmann distribution. Okay. So for example, the probability of finding something that's aligned with the field has a higher probability than it being anti-aligned. Okay. And this just follows this exponential distribution where this is sort of the energy. Okay. So the best example of this I've heard in terms of Boltzmann distribution, why this should be the case, is to think about parking in a parking garage, like say Gilman parking structure, where there's different levels, and so you could argue that this is the highest energy state, right? To get to the top level requires the highest energy. So if there was no parking permits, so like no A, B, S things, you could park anywhere you want. So if you were to come back and look at, let's say, 10 a.m. in the morning, you would tend to find a Boltzmann distribution, right? Most people, if they can park anywhere, are just going to park on the bottom floor, right? It's like, I'm just going to park, get out of my car, get with my day. But some people are like really excited and want to get to the top floor, right? And so, if you have more energy, you might go there. And some people are like, well, I'm sort of don't want to be on the bottom floor. I just want to be in the middle floor for some reason. So that's sort of a way to think about why you'll have an exponential distribution, okay, based on energy state. Okay, so what does that mean? That means that if I don't have a B0 field, then there can be a random sort of orientation. There's no preferred orientation for my little magnets, okay? And so if I took all these little spins and put their tail ends at the origin, I have what's called like a little cush ball, right? And so if you think of the vector sum of all those spins, what's it going to be? If I have random orientation of all these vectors, yeah, it's going to be 0, right? So they're all going to sum to 0. So then I'm going to have 0 net magnetization, all right? But if I put them in a B0 field, now there's a slight, there's an exponent, that Boltzmann distribution. So if I now sum them up, I'm going to get a net magnetization, okay? So that's basically the bottom line. So right now, even sitting here in this room, you are sitting in the Earth's magnetic field. So if we were to look at your net magnetization, each of you has a net magnetization, okay? And that net magnetization is processing at the Earth's Larmor frequency, which we'll talk about, all right? So that just means that this, and what happens is that magnetization, it turns out to be proportional to the B field. Okay. And this starts giving you a clue as to why people build bigger and build bigger magnets, which is if I want to make this signal bigger, I need a bigger magnet. Okay. And essentially it's a linear uh, relationship to first order, although it's not always linear. So essentially this is showing you the signal noise ratio versus field strength, and it's slightly more than superlinear because of other effects, but it's fairly, to first order, it could also be considered linear as well, right? So that's the primary reason where, going from 3 Tesla to this must be 9.4 Tesla, you're getting, in this case, like a factor of 5, right? Okay. Okay, so this is the part where we're now going to have to sort of go back to sort of freshman physics again and think about torque, right? And magnetic moment and forces and all that stuff, okay? So it turns out that um, if I have a B field and something with a magnetic moment, the torque or the tendency of this moment to align with the field is given by mu cross B. Okay, so just the right-hand rule will tell you that this is going to try to align this. So any orientation I start off with mu, there's going to be a torque that tries to get this to go from here to here. Okay, so that's just that equation. So I have a torque, and then from physics, we know that the change in angular momentum of my particle, of my magnetic moment, is going to be related to that torque. Okay. But I also said that the magnetic moment is related to the angular momentum with this relationship here. So I can plug this in here, and then I get d mu dt equals mu times gamma b. Okay, and this becomes the equation of motion for my spin or my magnetic moment. And what does that mean? If I'm lucky, this might, oh, that won't, okay. This is what I'll have to do next time. I'll have to bring in my bicycle wheel and show you this, but hopefully everyone is familiar with a gyroscope and everyone's ridden a bike, right? So it turns out that what this is going to do is this magnetic moment, if this magnetic moment, if it didn't have angular momentum, it would be like a compass needle and just go back to here. Okay, so if this is my compass needle, it would just align with the field. All right. But now imagine I'm rotating my Apple Pencil around its own axis, right? So now it has angular momentum. So it's saying if that's the case, then now it's going to go like this. It's going to precess around. Okay. So that becomes the fundamental thing that spins precess around the main field. Okay. So essentially right now, sitting in this room in the Earth's magnetic field, all your spins are sort of precessing, your protons are precessing. And I don't know what the inclination or declination, I don't know the direction of the magnetic field here. You can look it up online, but wherever that direction is, that's where you're spinning around. Okay, so let's get a little more back to notation. Remember, 1 Tesla equals 10,000 Gauss. Earth's field is about half a Gauss. And then the gyro-magnetic ratio for proton, this is for proton, for hydrogen protons is 26,752 radians per seconds per Gauss. Or if we want to get that into hertz, so we divide by 2 pi, it's about 4,258 hertz per Gauss. Okay, so that means in the Earth's magnetic field, if I wanted to know the Larmor frequency, let's get at that in a moment. We'll use this to calculate the rate at which the spins are precessing. Okay. These are just showing different ratios for different elements. And one of the things that we want to look at is one of the reasons why hydrogen proton imaging is the most popular imaging for clinical is the relative sensitivity of the measurement is very high. And as you go to these other materials, then the abundance goes down a lot, and also these gamma over 2 pi go down, and that just makes these less sensitive measurements. You can still do them, but they're not as sensitive. Okay. And then finally, we want to introduce Larmor frequency. So it's gamma omega equals gamma times b. So that's the angular frequency in radians per second. Or in frequency, it's gamma over b over 2 pi, gamma b over 2 pi. And this gives you the frequency in hertz. So for a 1.5 Tesla system, the lower frequency would be about 64 megahertz, right? And for a 3 Tesla system, then it'd be about 128 megahertz. Okay, so just for comparison, public radio here is about 89.5 megahertz, right? And then it goes the FM dial, if anyone uses FM radio anymore, but it goes to like 103 megahertz, right? Typically, or 105 megahertz. So if we look at a 3 Tesla scanner, it's at 128 megahertz approximately, which is in the civil aviation band. Okay, so there are lots of different frequencies bands, and this one, so this means that whenever you build these magnets, typically we have to put it in a shielded room. Okay, so we have copper lining the room so that interference doesn't come in to the room. Okay, and then we need to talk about, we've sort of talked about sort of a single spin on its own, but we need to talk about typically what we measure is the vector sum over many, many moments over a volume. Okay. So we can think of the overall magnetization from any given point in space as being the sum of all the protons in that space. And it turns out that because everything is linear and things superimpose, that then the overall equation of motion for this magnetization is also the equation of motion for any one magnetic moment. All right. So the bottom line is what you need to remember for this course is that the spins, the magnetization precesses, right? So at this point, from this point on, we're never really talking about any one spin. We're just talking about the collection of spins and its magnetization, right? Okay. So RF excitation. So the first thing we're going to talk about is why we need RF excitation and how do we do it. Okay. So the main idea behind RF excitation is we said we're going to have a net magnetic moment aligned with the B field. We apply what's called this RF pulse. So we'll apply an RF pulse. And its job, what it will do is it will take this magnetization and move it away from equilibrium. Okay, which sort of makes sense, right? You're taking a system that's very happy to be at equilibrium, right? And you put energy into it to get it to go away from equilibrium, all right? So this is what it looks like. So imagine this is our Cush ball with a net magnetization going this way. And if we apply an excitation pulse, so everything is precessing, right? And then that, as we apply that magnetization, it tends to move the whole magnetization away from equilibrium, okay? And the longer we apply that pulse, the more it sort of moves away from equilibrium. And then it'll sort of start coming back, okay? Okay, so the question is, we have something that's very happy to be at equilibrium. And we're going to come in with now this pulse, B1, which you can sort of see is perpendicular to the main field, B0, okay? This field here is super strong, okay? It's like 30,000 Gauss, okay? This field will tend to be very small, maybe like 0.2 Gauss, okay? It's like 60,000 times less, right? Because remember, we could just take a loop of wire and run current into it and create this B1 field as compared to this huge monster magnet that we created, okay? So we're trying to essentially like move something the size of an elephant with like a feather, okay? So that's the sort of order of magnitude difference. So here's some thought experiments. Let's say your neighbor, for whatever reason, put his car on a swing like this, okay? And you just happen to go over and if I said, go up to this car with your pinky finger, and if you can get this swinging, I'll give you $100. Okay. So how should you push this car to get the $100 without breaking your finger? What's the most important thing for you to know? Yeah.
resonant frequency so that each push is additive.
Yeah, yeah, right. Exactly right. Same thing when you push your friend on a swing, right? If you push them at the wrong time, you're going to break your finger, right? And if you push randomly, you're not going to move them. So you got to push at the resonant frequency. The same thing is if you imagined your friend was at a carnival or some amusement park and you are sort of here and you have a thread attached to them, right? And I say, I'll give you $100 if you can pull your friend off the horse, right? So this merry-go-round's going around, right? So clearly you're gonna have to run around with that person and exert a very faint pull. And if you do that and you can stay exactly the same frequency as the person, then you could have a chance of pulling that person off, right? That's essentially what we're doing with the RF field. We're essentially the field is very tiny, but if we apply it at the right frequency, it will tip the spin away from equilibrium, right? So what it looks like is this is going to be the magnetization and this is going to be the RF field. And if I play it at the, whoops, what happened there? If I play it at the right frequency, so this is on what we call on resonance, then you'll sort of see it's sort of like pulling your friend off that merry-go-round. It's able to get that magnetization down, okay? Now, here's the next example I'm going to play is now I'm slightly off frequency, right? It's essentially, let's say you're running too slow or running too fast such that your pulls are not efficient. Then what's going to happen is that magnetization is just going to sort of stay close to where it is. So for now, we're going to talk about ways of getting the magnetization down. Later on in the course, we'll talk about in some places you might want to leave it up, and in some places you might want to bring it down, okay? But the key is that the magnetization here, when it's at equilibrium, it's processing around, right? But for example, if you were like, it's sort of hard to tell, like if I could rotate this perfectly, right? It's sort of hard to tell it's processing, right? Okay. And in fact, the magnetic field, changing magnetic field created by this is almost impossible to tell, right? If I had a coil over here, there's no change in the magnetic field here, right? Okay. So, but if I flip this down and I make it process, it's really obvious that it's moving around, right? Similarly, if this is creating a huge changing magnetic field in this coil, okay? So that's why we want this precession to be tipped away. So then we have a signal we can sort of detect, okay? The other thing we're going to make use of a lot in this course is we're always going to sort of, as quickly as possible, move what's called to the rotating frame of reference, which is that if we don't want to have to think about things going at 130 million times per second, right? That's just hard. The math just becomes hard and it's really, confuses things. So essentially, the rotating frame of reference is very simple. Like if we're in the laboratory frame, if your friend is on the merry-go-round, right, it appears as if they're moving around, right? But once you hop onto the merry-go-round, it looks like they're just standing still, right? So that's the rotating frame of reference. Same thing, we're all on this Earth. We're all moving, I don't know how many thousands of miles per hour, right? But it looks like you're stationary, right? Because we're all in the same rotating frame of reference. So for the spins, we're going to want to hop onto the sort of the reference frame of the spin, okay? So if we're in the laboratory frame, it would look like the spin spirals down like we saw in the simulation. But in the rotating frame of reference, it looks like the spin just goes from here to here, okay? So this is showing you what the magnetization looks like in the rotating frame of reference. Okay. So for pretty much, you can always assume whenever we talk about things in this course, we're assuming we've done all the math to get into the rotating frame of reference, right? Okay, so the first thing we're going to do introduce in terms of a calculation is what's called the flip angle. Okay, so the flip angle is simply what angle have you moved the magnetization away from its equilibrium point. And probably the most common flip angle, at least for beginning discussions, is we're going to assume we want to flip it to 90 degrees. Okay, there we get the maximum sort of magnetization. Okay. Now, we'll see later in the course that there's advantages to flipping it maybe 20 or 30 degrees. Okay. but for now, 90 degrees, and we'll see even later, sometimes there's an advantage of flipping it 180 degrees. Okay, so flipping it all the way around, all right? So this flip angle, don't assume it always has to be 90 degrees. It can have many different values. Okay. And the way we calculate it is we say, well, what's the frequency of change of that magnetization? And we just integrate that frequency over time to get the overall change in the angle. Okay, and that frequency is just take gamma times the B1 field. And this is essentially, that's the Larmor frequency generated by that B1 field. And that's going to cause a precession, right? Okay, remember any field creates a precession. So this is just creating precession at that frequency. And then we integrate that frequency to get the overall flip angle. So here's a very simple example of, we'll do our very first pulse sequence diagram. So this is a function of time. This is the RF amplitude. This is 400 microseconds, right? And my design goal is I want a flip angle of pi over 2. Okay. And so I want to ask, what should be the amplitude of my B1 field such that I get that pi over 2? Okay. And this is, we're assuming we're just playing out a rectangular pulse. Okay. So we know that omega 1 equals gamma B1, right? That's our Larmor frequency from the B1 field. Okay. And now we're just going to integrate omega 1 over time from 0 to 400 times 10 to the minus 6 seconds, right? And that's going to be my theta, right? But this just equals gamma B1 times my 400 microseconds, right? So I know what my theta is. I know what gamma is. I know what this time is. So then I just solve for B1. All right, and that's what's done here. So if I do that, then theta equals B1 equals theta over gamma times the duration of my pulse. I just plug everything in. I get 0.1468 Gauss. Okay, and so that's about 1/3 of the Earth's magnetic field is the size of the field I need to apply to get my flip angle, to get the magnetization to flip from 0 degrees to 90 degrees in 400 microseconds. So very, boom, just like that. Okay. So every MRI pulse sequence is going to have something like this, where we're going to flip the magnetization, right? Okay, so yeah, this works out. So well, what I like to do is sort of, ideally this would happen more towards the middle of the lecture to give you a break, but here it's good. We have about 10 minutes left, so we can take a few minutes for you to look at this question. And the way we'll do it is feel free to talk to your neighbor or whatever, and you're just asked to pick the closest answer. To keep things simple, you can assume that gamma over 2 pi is 4,000 hertz per Gauss. And we'll come back in a few minutes to sort of see what people think the right answer is. And for the people on Zoom, I'll open up a poll so you can pick the closest one. Okay. Polls. Okay, about another minute, and then we'll see what people think. Okay, so what we're going to do is for everyone in class, uh, I'm just going to count to three and just say very loudly what you think is the right answer. I'm going to close my eyes and do sort of an average and sort of think for C. Just that's faster than doing any sort of polling, right? So I'm closing my eyes. One, two, three. Okay, very good. Yeah. Okay, so let's see how we do that. All right. So I think F is the right answer, but let's work through that just so everyone's on the same page. So first of all, let's look at this RF pulse, right? So it's a amplitude of A, and it's got the form A sync T over big T. Okay. So one thing is that this is a very, very common RF pulse in MRI. It's probably right now, this pulse is being, some sort of sync pulse is being played out on almost every MRI machine in the world. So however many tens of thousands of MRIs are being done right now, this is a sync pulse is being played out. And we'll learn later why sync pulse is so important, but this is a very common sort of thing. So we know we need to take the area of that sync pulse, right? So we know somehow we need to know what that area is. Okay. So how do we get that area? Any ideas? No one wants to integrate that, right? Okay, so what's the trick that we want to apply? Like, how did you guys figure this out? Right. So what is the area of that pulse? Anyone? Okay. So here's a clue, right? It's what is, if I write this, right? E to the minus j 2 pi f of t, what does that look like? That's the Fourier transform, right? That's the Fourier transform, right? Of my object, right? So what's the Fourier transform of a sinc function? Rect function, right? So we apply the scaling theorem. We know the Fourier transform is equal to A times T rect of F T, right? By applying the scaling theorem. And I want to apply this at F equals 0, right? Because if I at F equals 0, this term is equal 1 at F equals 0, right? So therefore, I know that what's the rect function at 0? Value of the rect function at 0? 1, right? So this is just A times T. Okay, so that's a good little fact that's good to keep in mind. So now I know I want to just say pi over 4, or let's say we want pi over 4 is our theta, right? We want that to be equal to gamma times A times T. Is that right? You get that right? Okay. So this just means that the amplitude is equal to pi over 4 over gamma times T, right? Okay. So that equals pi over 4 over, we have 4,000 hertz per Gauss, but then we have to multiply that by 2 pi to get gamma, right? And then we divide by 250 times 10 to the minus 6. Right? Sorry, this is getting a little messy. Let's put it over here. So the pi's divide out. So I have 1 over 4 times 4,000, 250, 1 times 10 to the minus 6, right? Okay, so can someone calculate that? What is the answer? What is it? Anyone have does someone calculate this for me? Let's see, that's 1 over 1 times 10 to the minus 3, 4,000, is that right? So 1,000 over 4,000, right? Did I do my math wrong? Let's see. That's 250, right? 250 times 4 is 1,000, right? So then I get 1 times 10 to the minus 3, and then that's 4,000. So I have 1,000 over 4,000, but that would give me like, what's 1 over 4? 0.25 cows, right? So did I miss a factor of 2? Oh, there's a 2 pi, right? Okay, yeah, there's a 2 pi. Right, so 0.125 Gauss. Okay, so everyone got that? Okay, so what you'll find is this course actually, that's the level of math you have to do, right? That's really all we're going to be doing is like integrals of areas. But you'll find out that even though all the underlying math is super simple, keeping track of everything can be a little confusing. So the best thing is just work it out, do it. Everyone can do the math, but it's just we have to have areas of RF functions, you have areas of gradients, and then putting it all together is sort of what creates the magic. All right, so that's all for today. We'll pick up again on Wednesday. The only thing that's going to sort of slightly change now is that I will use after this class, I will post the first pre-lecture quiz. So typically, those are just going to be typically about 4 questions that you can, if you watch the lecture, should be relatively straightforward to answer. It just helps you sort of reconsolidate your understanding after every lecture. And those are typically due like, I think 10 a.m. the day of the next lecture. So basically, and so I'll post an announcement about that, and that will just, and there's a really funky grading scheme where you're mostly, if you just do the quiz, you get most of the points, and yeah, so it should not induce stress, hopefully. Yes, question.
Is this part of a participation?
Yeah, this basically determines your participation. Yeah, for the most part. Yeah. Question.
Should we have been having to do those like for this, right?
Not that I'm aware of. I haven't seen any, but if there are, I guess, yeah. Okay, but I don't think so, right? Okay, right.